In this presentation, we'll be talking about detecting errors in databases with bidirectional recurrent neural networks. My name is Kurt Stockinger, and I'm from Zurich University of Applied Sciences in Winterthur, Switzerland. This is joint work with my colleague Severin Holzer from the Statistics Office of the City of Zurich. Let's first introduce the problem of detecting errors in the database. And let's look at an example about information of people. Let's assume here on the left side, we have a dirty table. On the right side, we have a clean table. So there's, for instance, information about the ID of a person, the salary, the zip code, and the city, okay? And here's one specific error. Let's see, we have a comma in here in the value, and this could be a synthetic error or a value error. On the other hand, on this side, there's no comma in there, okay? Another error could be that the city name is not known, so it's a missing value, or Rome is misspelled, so here's an R, here's an E, or that the ID is wrong, a zip code has some wrong entry in there, the salary is wrong, or here a specific zip code, for instance, this would be the zip code of Paris and not of Vienna, okay? So how can we solve this problem? One approach is to use recurrent neural networks for detecting errors in the database. And this is a so-called sequence-to-sequence model, and they have been very widely used in natural language processing, especially for some tasks such as machine translation or language generation, okay? And the intuition is that you take the input and then make prediction about the previous input for the subsequent one. Assume an example, you want to translate the sentence, the girl plays in the garden, and now you want to translate this English sentence into German or into French. Okay, so you take each of the words and make predictions about what the next word could be while you translate the sentence. Okay. This approach has been widely used already in machine learning and special natural language processing, and it works quite well. The disadvantage is it requires a lot of training. And in our database setting, where we want to detect errors in the database, typically we don't have so many training data, or we don't have so many labels. So we basically need an approach to select those records and label them afterwards by a human, such that the requirement of the labels is actually minimized. Okay. How do we approach this problem? First, we need to encode our database records and assume we have here the word BASI, and this is an example of how we could encode it. So first we need to find an alphabet of how we could encode the specific word. So for instance, A would be encoded as 1 and B encoded as 2, C as 3 and so on. And next you take this alphabet and then you encode each character according to the alphabet. So here, for instance, we have the characters B, A, C and Y, and here we have the characters that are embedded. And in here we have the numbers which are learned by a machine learning model to represent these characters. So the intuition is that characters that are similar are clustered together and dissimilar characters are far away from each other. So this is also known from word embeddings, for instance, that is used in natural language processing. Next step is that we design the neural network architecture. And for instance, here on the left side, we have again a value that we want to encode. In this case, it's A3, and this is the character embedding. So all these characters come into our neural networks, then they are embedded. Here's one layer of the recurrent neural network, here's the other one. And all these are then the several characters that are embedded independently. At the end, they all need to be combined again into one vector. Then they are connected again with a fully connected neural network. And then in the end, the neural network has to decide, is it an error or is it not an error? Okay, so we basically turn the error detection problem into a classification problem. Okay, we experimented also with another architecture where we said we not only encode the value, but we also give information about what attribute it is. So for instance, attribute 2 could be the name and attribute 4 could be the city. Okay, so we provide this information as well, pass it through a recurrent neural network layer, then we combine the results, and then we can combine basically the vectors from both of these approaches so that we make the neural network learn this information. The problem, as I said previously, with recurrent neural networks is typically they require a large amount of training data, but we want to define an algorithm that selects those records and label them afterwards that have the maximum amount of impact for the training. So basically the intuition is we select tuple values that we have previously not seen because they basically increase the information content, and the higher the information content, the more and the better we can learn using a machine learning approach. The algorithms is described here. You can look it up in the paper. So next is we evaluated our approach. And here we use publicly available data sets. For instance, there's the beer data set or the flights data set. This one consists of about 2,400 rows and about 11 columns. And you also see the error rate of these data sets. So for instance, the hospital data set has about 3% errors in there, whereas the flight data set has about 30% error. So it has a higher error rate, which might be, it's a different approach and different complexity, okay? We also see how many different characters they have in there and also what error types are in the data set. So for instance, MV is a missing value or VR is a formatting issue, okay? Then we compared our approach against the state-of-the-art systems. One of them is Raha from Sigmod 2019, and the other one is Rotom from Sigmod 2021. And what we did, we compared the F1 scores of basically our machine learning approach to detect errors, but we only chose 20 labeled tuples. Okay, so we had a very little training set and we compare the approaches. We can see that in some data sets, for instance, Raha is performing best, in another one, Rotem, and in another one, our approach is performing better. Okay, so here we don't really see a clear picture who is the absolute winner and what's the best approach. So that's why what we did the average F1 score over all data sets. Okay, and we have done two versions. One is without flights, because for instance, Rotom does not evaluate on the flights data sets, and the other one is with flights. And if you take the average score over all data sets and then measure the F1 score, we see that our approach slightly outperforms basically the other approaches. What is also important, our approach has a lower standard deviation, and standard deviation is basically an error rate, right? So we have a lower error rate across all these data sets, which means that our approach is a bit more robust than the existing ones, okay? And we see the advantage of the F1 score both for the data sets with flights and also without the flights. So to summarize, we introduced two-stack bidirectional neural networks for error detection. We evaluated them on six publicly available data sets, and we have shown that we have a higher average F1 score and a lower standard deviation. And we're currently also working with an industry partner to apply this approach in a real world setting.